Once you've unpacked the RX1 kit, the next step is the assembly. In the manual there is some suggested assembly steps which you might like to follow. The first one is mounting the components on the noise board. There is also an overlay diagram showing that circuit, the noise generator board. Use that in conjunction with the circuit diagram if you need to help you identify where the components go. I've taken the components out of the plastic bags and I put them in this little tackle box. This is the noise generator board, and I would suggest the first area you start is by mounting a small 3mm nut in the middle of the board. That nut gets soldered in. You should first clean the edges of the nut with a file, then tin it. Once it's tinned, tin the board, solder the nut to the bottom of the board. When attaching the nut to the bottom of the circuit board, use a small bolt temporarily to hold it in place. Having done that, install fit the various resistors, the low profile components, the Zener diode, followed by the capacitors, trim pots, semiconductors in their foam pack. Keep them in the foam pack till you're ready to solder them into the circuit board, electrolytic capacitor and terminal block. Once they've been mounted, there's no reason why you can't test the board. This is what the board looks like once you've soldered all the components in. This is on the prototype, and you'll notice that there is a terminal marked with some reg texta. That's to help me identify which is the positive terminal of the board. That is the terminal that takes the positive voltage from the battery. If you reverse the connections to this block, you may destroy the transistors. The board itself mounts inside the case quite simply with one screw. There's a hole in the side, and that screw locates with the nut that you soldered to the bottom of the board. Here it is here. I'll just attach that very quickly, just show you how easy it is to fix. That's it there. That's what it looks like once it's in. You'll see the nut there. There's the hole on the side. There we go. And the little cable going to the RCA connector at the rear of the case. Here is a view of the bottom of the board, and you can see the nut soldered in place there. Step 3 of the assembly instructions is to mount the base PCB into the bottom of the box. This is the base PCB. It's just a blank piece of fiberglass board with four holes drilled in it. The 4 holes match with 4 holes in the bottom of the box, which have been countersunk. Once you've mounted the base board into the box, and you can use some screws inside the little packet of screws. There are some countersunk screws attached to pillars. Those countersunk screws go into these 2 holes here, so use them temporarily with some nuts to put that in place. Once you've put that in place, you can then mount the rear connector panel. The rear connector panel has 4 connectors on it, and these go in the holes as such on this side of the board. Two connectors are on one panel, the RCA connectors. Go like that. They get mounted to the board, and the panel goes in the back of the box, sitting on top of the baseboard like that. 3 holes are in the back of the case which hold the rear panel in place, and there are some 4mm nuts used as spacers. Now I'll just show you the already assembled prototype just to save time. Here it is here. We'll just come in tight on the rear panel. You'll see the 4 connectors there, and I'll just swing that round so you can see the 4mm spacers and the screws on the other side that come through. The ones with the 4mm spacers are 16mm screws. The other ones are 10mm. Once you've mounted the connectors on the panel, you can solder the panel to the bottom of the box, to the baseboard. Just 3 spots should be sufficient. One in the corner there, one in the middle, and one at that end. One thing you should do when mounting the connectors is tin the area around the bolts. The circuit board is covered in a protective lacquer. If you don't tin the area around where the screws are going, there won't be an electrical contact between the body of the connector and the ground plane. So just make sure they're all neatly tinned. Use a bit of solder wick or something to just flatten the solder off. As you can see there, you don't need a lot of solder, just enough to make contact. All of those screw holes have all been had a little bit of tin put around them. The same applies to the baseboard, where the aluminium bracket goes later on. Down these two holes here towards the front of the case require a bit of tinning. The next step in the assembly process is to mount the RF deck inside the case. I'll just show it to you here. There's the RF deck, a bit tighter there. Okay, before you mount the RF deck in the case though, I would suggest you mount the transformer on the circuit board first. Here you see it mounted with a zip tie, and in the kit you'll find a balun coil and some 0.3mm wire. 3 pieces of wire, 144mm, are cut from that. They go to make up the primary and secondary of the transformer. There's the 3 wires that go to make up the transformer. I've left these two joined together. You can use a small chuck to grip the 2 leads at the point where they fold over. Then using a small screwdriver or similar electric screwdriver, just twist them together. You require roughly 6 twists per inch. Just use a ruler to check that. So here you can see the twisted wire up against the ruler. 1, 2, 3, 4, 5, 6. You see the brightened up parts of the wire under the light. You see 6 twists per inch. We start by winding the secondary first. We pass the twisted wires through the balun coil to make 3 turns. I've just put the joined end this side, just folded it over so it doesn't get in the way. That is 1 turn. 1 turn is defined as going through the holes once. We now have 1.5 turns, and we try and keep those loops a bit tight so they don't start to unravel. It's 2 turns, and we've got to watch these little open ends that they don't catch inside on other wires. Okay, it's 2.5 turns, and finally the last bit. So we now have 3 turns on this transformer with enough wire on each end. We now wind the primary using the single piece of wire. The wires for the primary come out of the other side of the transformer on this side here, so we just pass the wire through, tuck it in through there. It's 1 turn, again 1.5, 2, 2.5, and finally 3 turns. So there's the primary. There's the inside of the coil. Plenty of room. There's the secondary. At this stage we still have the join there. We'll cut that join in a minute. We need to identify the wires using a multimeter. First thing we do is just tin the ends with the soldering iron. There it is. So with a multimeter we just check the primary, that's okay. Now we're looking for the secondary, number 2, 2 start, and we find it matches up here. So that's 2 start, 2 finish. So this one has to be 3 start and 3 finish. 3 start and 2 finish joined together. That one there is 3 start and that one there is 2 finish. So we just join those two together, twist them together like that, and that makes the center tap. And with the soldering iron, just join them up. Now we just checked we don't have any short circuits between primary and secondary due to kinks. Just attach the meter there. It's okay. And we'll just check the secondary. That's okay. So we've now finished the transformer. Having made the transformer, you can now zip tie it to the RF deck, as you can see here. Just makes it a bit tidier. Once you've zip tied it to the RF deck, you can then mount the RF deck inside the case. The RF deck mounts towards the rear of the case and it's held in by 2 pillars to the bottom baseboard. Once you've attached the RF deck with the pillars, solder it to the rear panel in 3 places. Over here, here and here. There we go. There's one connection there. There's one behind that trimmer and one underneath the RCA connector there, coming into view. Once you've soldered the RF deck in place, you can mount the various components. There are 3 trimmers, 2 small ones and 1 large. You'll see them there, and the compensation coil, which is 4 turns on a 4mm drill, or thereabouts. You can see it there. Oops, out of focus. There's the trimmers mounted, and there's also a ceramic capacitor C10, which is 82 picofarads in there, between that land and that land, going to the Z unknown connector, which is this one here. The receiver, that's the receiver connector. The transformer can be wired in. The center tap goes to the spigot for the receiver. One wire of the secondary goes down here to the compensation coil and trimmer, and the other wire goes down here where the other trimmer is. The primary, of course, goes to the RCA connector. You'll see the earth goes down near the RCA connector earth, or one side of the primary, and the other side of the primary goes to that connector. When soldering to these RCA connectors, put a dummy plug in the socket. See, I've got a plug in there now, which is actually the loop, and that keeps the center spigot from moving around when it gets a bit hot and melts the plastic. Similar thing applies to these PL259s. Put a plug or something in when soldering. You'll see on the receiver one there's a small piece of wire going from the center tap of the transformer to a pad and then up to the spigot. Here it is there. And on the Z unknown connector, I've just simply folded the ceramic trimmer lead up so that it acts as a bridge as well. You can see that there a little bit, hopefully. Once you've mounted the RF deck, you can assemble the control board. The control board has a tuning capacitor and a potentiometer on it. It also has 2 resistors, a couple of LEDs and a little terminal block. The LEDs and terminal block potentiometer can be mounted on the board first. Once the board is assembled, it's attached to the bottom of the box with an aluminium bracket called the control bracket. The holes in the aluminium bracket have been drilled a little bit larger than 3mm, and that is to allow you to adjust the position of the control board in various directions, up and down, sideways, etc., so that the shafts are nice and straight. If you find you don't have enough adjustment, just slot the holes a little bit with a small file, but there should be sufficient adjustment there. Once the control board's put in place, you can attach the brass couplers, potentiometer and the tuning capacitor. Slide put these dial drums in, attach the paper scales to the dial drums using a bit of double-sided tape. Slide the plastic shafts through, put 2mm bolts through to keep them in place. The shafts and couplers and pot have been drilled together so that the holes should line up without any problems. There you go, there's a bit of view. Both have plastic shafts, and then you can attach the knobs using a hex Allen key to tighten the grub screws up. Once you've done that, solder a wire from the top of the pot down to the RF deck. Don't forget that wire. If you forget that, of course, it won't work. Just some point to make is that the back of the potentiometers are marked with a number. This number represents the resistance between the ends of the pot. I have found that these particular pots can be anything from 500 ohms to 560 ohms. The dial scales have been generated using 540 ohm pot. I find that between 520 and 560 the dial scale is not too bad, so it would seem. These pots are not very expensive. However, if you want to improve the performance of the bridge, you can always use a pot like this. This is a Bourne's pot. They cost around $20. They're a Cermet pot, not that easy to get, but I have allowed enough room in the box for you to substitute a better quality pot. These happen to have a plastic shaft, which is also a benefit in reducing stray capacitance. Likewise with the tuning capacitor. The tuning capacitor is not an expensive tuning capacitor, as you can see. Both of these items do the job adequately for what this kit was designed for, which is for students, and we've tried to keep the cost down by using these components. This particular tuning capacitor is one that you can buy from overseas. They also cost about $20 to land. By the time you pay the exchange rate in the mail, could be even $30. Whereas these little tuning gangs are only a couple of dollars. So we're looking at about $4 versus probably $40, which would add quite a lot to the cost of the kit. And you'd have to, for students, it may not be warranted. Of course, you can of course also find low-cost tuning capacitors at swap meets. This is one out of a broadcast radio. Now again, I've left enough room in the box to mount these components. However, you may need to think about how big these wheels need to be, and if you find that it doesn't fit with your particular components, some noise bridges have scales around the knobs. Just depends how accurate you want the scale to be. So I've made the box reasonably large to accommodate these changes. You'll also need to mount the power switch, and the power switch comes with a tiny circuit board, which is just 3 strips of copper, which is shown like that. You will see in this section here the battery snap connects to one strip. Then there's a wire from the positive of the battery snap up to the pole of the switch. The other side of the switch goes to a Schottky diode, the anode of a Schottky diode. The cathode goes down to this strip, which then feeds the power to the LED board and the noise board. Again, the reason for that diode is just in case you accidentally touch the wrong terminals on the battery snap with the battery holder and thereby blow up the transistors. It's a precaution that I believe is necessary. The Schottky diode has about 0.25 of a volt drop across. It's not a lot. Normal silicon power diodes probably around about 0.6 of a volt, so you don't lose too much out of that. The switch is mounted through a hole in the front, and you can see I've taken the washer and bent the tab up. I'm not using that to keep the switch from rotating, and I've only used the one nut on the front. There's not enough room with this particular switch to use the rear nut as well as the front nut. Once you've mounted the power switch, there's also a battery shield which has got some cutouts to allow the wires going to the noise board and the control board to pass underneath. Okay, the wire passes underneath and goes across to the noise board and comes out over here. And that just gets tucked in like that. There's also a short lead, a short shielded piece of wire going from the noise board to the rear RCA connector, and that takes the noise out of the noise generator board through the loop and into the bridge. This loop can be removed, and you can add an external signal generator into here. The external signal generators mean that you can use, instead of a receiver as an outlet, you can use a diode and a meter, but most external signal generators don't have enough power to give you a good reading with just a diode and a meter. You usually need some sort of DC amplifier to go with it. That can be useful for some tests. Once you've mounted the power switch, you can fit the battery holder. I've left plenty of room here for a variety of batteries, but I prefer the AA's. They're quite cheap to get, alkaline or rechargeable AA's, but the alkalines give you the 9 volts. And there's plenty of room in this box if you want to change that. Put a little bit of foam packing around the thing, and just make sure there's some form of insulation between the back of the battery holder and the switch, so that if the battery touches the back of the switch, it doesn't short part of the battery system out. So a bit of insulation in there, a bit of cardboard, and a bit of foam packing around the battery to stop it rattling around. Once you've attached that, you're really ready to start testing the unit. I've included some LEDs for effect over the dials. You can move the LEDs around. I've left the leads a little bit long, just so that you get a nice little beam over the centre of the scale. That's the blue one, and the green one. These are high brightness LEDs. There we go, and you can just adjust the beam to suit. When you put the lid on, it tends to move a little bit. We'll also need to make a small loop for the back of the box. I've included heat shrink of various sizes so that you can make it a neat job of that. There's bits of heat shrink inside there, and a couple of little metal RCA plugs. Just plug in the back here like that. Well, the last step before testing is to put the cursors on the case. The cursor is just a piece of plastic transparency with some lines on it and a couple of circles. Line the circles up with the holes in the case. Just use some pieces of double-sided sticky tape, which I've included in the kit, to hold it in place. You can attach the scale, the front panel label, which indicates what the functions of the dials are, and the connectors. There's also some charts taken from the spreadsheets, which are included in the kit as software Excel spreadsheets. I've taken some picture grabs, and these are the reactance readings at 10 megahertz for positions of the resistance dial and the reactance dial. Well, actually, it's just the reactance dial. This is the capacitive reactance, and this is the inductive reactance part. So they're just handy, so saving you have to look up a chart or anything. And by noting the reactance at 10 megahertz, you can calculate the reactance at other frequencies by using a ratio. Fit the handles. The handles are there for to complete the project, actually, just to give it a bit of a touch. It just fits in there. There are 4 screws in the kit with 4 little rubber caps which go over there. Put them in last. You will need to calibrate the bridge, and during the calibration process the lid is going to come on and off as you line the cursors up with the various dials. There we go. I turn the LEDs off because they interfere with the camera. There we go. And that one there. You can make your own dials if you change the capacitor or the potentiometer, or you want bigger numbers or different colours. I've included a PDF on the disc with the dial dimensions. You can reprint that. Make sure your printer is set to produce a 1:1 scale. Some printers, if you print to the margins, will reduce the scale by about 5%, I've found. So just check that. There's a dimension on the drawing, and of course that dimension will change with the type of potentiometer or capacitor you've got. And that's it. Next step will be the testing and calibration.